Hey everyone, and welcome to this explainer. Today, we're going to explore some literally mind-bending science about the very nature of light itself. The whole purpose of this explainer is to unpack a really fascinating, novel, falsifiable hypothesis. It's one that attempts to finally explain something called orientation-conditioned relative phase in weighted light modern networks. Now, I know, that sounds like a massive mouthful of heavy science jargon, but don't worry, we're going to break it all down step by step so it's clear, visual, and super easy to understand. Think about light just traveling from point A to point B. Standard physics tells us a ton about how that journey happens, right? But we kind of have to ask a deeper question here. Does the specific path light travels somehow change its fundamental nature? Like, is it actually possible that navigating a really specific shaped path gives a tiny particle of light a unique, hidden twist that our standard rules of physics are just totally missing? Well, that is the exact mystery we're unpacking today. Okay, let's dive into this. Here is our clean, 5-step roadmap for today. Number 1, the core quantum problem. 2, a novel light hypothesis. 3, testing the triangular network. 4, rules for falsification. And 5, real-world implications. Starting with part 1, the core quantum problem, finding the photon. So before we can talk about what might be new or hidden in the physics world, we really have to establish the baseline of what we already know about light. Standard QED physics is basically our established rulebook, and it's incredibly good at calculating how light bounces off mirrors, passes through glass, or bends inside a lens. But there might be a missing piece. Even with all our amazing cutting-edge optical technology, could the specific shape of the path light takes, what physicists call an interaction network, actually add an unknown shift or twist to the light? And to be clear, this isn't about the material the light passes through, it's about the actual physical geometry of the path itself. Which naturally brings us to a major ongoing mystery in physics known as photon localization. Simply put, even with our absolute best math, it is incredibly hard to define exactly where a single particle of light, a photon, actually is at the precise moment we measure it. It's kind of like trying to photograph a speeding bullet in the pitch dark. Because standard physics still has some fuzziness around this specific localization problem, it leaves a door cracked open. It literally means there's room in our scientific understanding for undiscovered rules about how light behaves when it interacts with complex physical spaces. Moving on to part 2, a novel light hypothesis, the traffic intersection. With that core mystery in mind, we turn to a brand new architectural blueprint that attempts to solve this exact problem. This quote right here is basically the foundation of our entire explainer today. We really have to credit researcher, inventor, and author Kevin L. Brown for this novel falsifiable hypothesis. He proposes that an oriented, weighted, 3-link interaction network might add a totally new relative phase to light. Now, it's really important to note that right now, this is a theoretical proposal. It's a brilliant idea waiting for an experiment, not a claim that it's already been proven in a lab somewhere. Now, you might be wondering, what exactly does orientation-conditioned relative phase actually mean? Let's drop the jargon. It simply means that light gets a unique twist, a change in its phase, based entirely on the shape and the direction of the physical network it's passing through. Again, it's not about what the network is made of, like glass or fiber optics, but how it's structured and oriented in space. To really grasp this without getting bogged down in heavy math, just think about a 3-way traffic intersection. Imagine a single particle of light is like a car driving into a triangular setup of roads. Brown's hypothesis asks, does the physical shape of that intersection somehow alter the car itself? Like, if you take a specific sequence of turns around that triangle, does your car exit the intersection with a new measurable twist that you absolutely wouldn't get from just driving straight down the highway? That brings us to part 3, testing the triangular network, catching the twist. Ideas are great, but in science, we actually have to test them out. To validate this hypothesis, the author outlines a very specific trap, an interferometer, which is essentially just a highly precise light-splitting device. And it works in 3 logical steps. Step 1, we shoot a single photon of light into a balanced splitter, perfectly dividing the light's probability. Step 2, we pass it through that special 3-path triangular network we just talked about. And step 3, we catch the light at the end with a detector to measure its final twist, or what physicists call contrast. If the detector shows a change that standard physics just can't explain, well, we might have just caught our twist in action. Now, the number 3 is absolutely vital here. The entire experiment relies on 3 distinct physical pathways. The network has to have 3 links. If it has 2, or maybe 4, the specific mathematics of this shape-based twist just do not work. It's the unique geometry of a triangle that supposedly triggers this hidden rule of light.
On to part 4, rules for falsification, the ultimate gauntlet.
You know the secret to really good science, right? You don't build an experiment just to prove your theory right. You build it to try and prove it wrong. Brown's paper provides a really strict list of decisive rejection triggers. If any of these happen, the hypothesis is thrown out entirely. First, if standard physics can already explain the twist, the theory is rejected. Second, if we flip the network like a mirror and the light doesn't perfectly reverse its twist, rejected. If we turn the power to the network completely off, but we still see a twist, rejected. And finally, if making the network stronger doesn't cleanly scale the twist up, you guessed it, rejected.
So the crucial point is really laid out in these mandatory controls. This is the ultimate gauntlet. Look how incredibly strict this is. If the network is off, the result must be exactly 0 phase shift. If the triangle is perfectly symmetric, again, exactly 0. And if we physically mirror reverse the paths, the twist must be the exact mathematical opposite. Failing even one of these tests kills the theory immediately. And honestly, this strictness is exactly what makes it such a highly credible scientific proposal.
Finally, part 5, real-world implications. Are we entering a new quantum era? So what does this all mean? Why does all of this matter to us? Well, it brilliantly illustrates the beauty of science. If this test actually survives that brutal gauntlet of controls we just talked about, it wouldn't mean standard physics is broken. Not at all. Instead, it adds a completely new layer to our understanding of informational physics. It would prove that the mere physical shape of an interacting network is a fundamental feature that changes the behavior of a photon. It basically expands the rulebook. Which leaves us with a pretty thrilling question to ponder. If it turns out that the simple shape of a path fundamentally alters a particle of light, how will this hidden twist change the future of quantum technology? Could this lead to insane new quantum computers, vastly better sensors, or even entirely new ways of transmitting information? The experiment is just waiting to be done, and the results could open a whole new door in physics. Thanks so much for learning with me today, and keep exploring the incredible, structured universe around us.